So, music theory, when you're really getting into it, you'll find out is like an exponential thing. Things are all going to work, at least in 12 tone, by, numbers of 12. So you can end up with, having 12 to the power of 3, 12 to the power of itself. So, a good way of kind of condensing a lot of our music theory is going to be through a method called tetrachords. And for 12 tone music, I'm going to list 11 tetrachords that are going to give you 144 options for other tetrachords. So in total, that's going to be, sorry, let me grab my pen real quick. Always got to have a pen on you. Hand swap on the iPhone, forgive me. All right, back to our momentum. All right, in total, you're going to have 1,584 tetrads. Just write that out. Maybe I have that written down already, but get used to this number, 1,584. Anyway, the reason tetrads work so well is because we can make every tetrad into a polynomial with degree 3, and we can have tetrads which represent polynomials, which look like this. So our tetrads are all going to have a main coefficient family, and our big 11 are going to be all units over 6, so 1/6 x cubed, 1/3 x cubed, 1/2 x cubed, 2/3 x cubed, 5/6 x cubed, and 1 x cubed. And then to get the other 5, just going to have 1 in front of it, and we're not going to get to 2. And that's because in our modulus, 2 is going to equal 0, and it would be redundant to write 0 minus 0. And our prime form is going to look like this, ax cubed minus ax, and this is the polynomial which we're going to build all of our other families off of. This is kind of the explanation. I have it kind of divided up into tetrad, super tetrad, and hypertetrad. And basically our tetrad starts out with this. And how we get this is we find all the derivatives of this sequence. And this sequence is going to give us a polynomial that looks like this. And sorry, this is prior to this video, but let's just say plus or minus. And when we take this and we put this, sorry, forgive me for the camera movement, but when this is our tetrad, and we have the derivatives of our tetrad, and then we have the integrals of our tetrad, this is going to give us our tetrad structure, which gives us our monad, our dyad, our triad, and our tetrad. And this gives us what I call the initial conditions, these variables which we put in to get our polynomial to give us our tetrad and our integrals of the tetrad. And then you can, as you see from the negative sign, you can make it negative, and that's going to give you the inverse tetrad. So if our constant is here, this is going to be a major 7 instead of a flat 2, and all these are going to go to their natural inversions. And that's coming from this structure here, the prime retrograde, inverse retrograde structure. And another important note from this page is that these are going to extend infinitely in either direction according to this sequence. So a super tetrad is just our classic Greek tetrad structure with the derivative. And then when we have our prime super tetrad and our inverse super tetrad, we get a hypertetrad. This is a reference for a major 7 tetrad. So, and this is also explaining how you can just use it in regular music notation just by writing something like C major 7, where taking our pitch, which is C, and our set, which is major 7, and we're going to extend our set to look like this. So our major 7th tetrad, our major 7th triad, our major dyad, and our root. And then here's the derivatives, how we get the major 7th chord. And then of course they can be extended in any way here or here. So we can get our inverse tetrachord if we want, and make a hypertetrad. And of course tetrad equals tetrachord, so if I incorrectly am saying one or the other, they just mean the same thing. And then in music we can take this set and we can just repeat it with a different pitch. So we can have C major 7, and then we can have, F major 7. And we're just taking these intervals, all here are set, and we're just multiplying that by the pitch, meaning we're just going to start, our root is always going to be, C or F. The root is relative, but these intervals are going to belong to our set. So I mentioned 11 tetrads that we can get 144 other tetrads from, so 1,584 tetrads possible. Here they are. This is going to be 16x cubed minus 16x. And so here we have root. Here's our initial conditions. And an important note to make, I'll just write it down somewhere here. For our prime form tetrads, our initial conditions are going to alternate. So I'm writing this out like a doctor here. But for prime tetrads, our initial conditions alternate. So I'm going to repeat that again. For prime form tetrads, our initial conditions alternate. So you see we have a minor second here, a major second here, and a minor second here. A major second, major third, major second. C major second, this would invert to be a minor 7th. This would be a minor second, this would invert to be a major 7th. That's the alternating format. And so these initial conditions give us this equals this, and then with our integrals, we're gonna get this as our set. And this is gonna represent our prime form, our semitone family, our 1/6 family. And this is basically, just think about this as like a derivative of the chromatic scale. This is a derivative of the whole tone scale. Derivative of the diminished 7th chord. Derivative of the augmented triad. Chromatic scale. Tritone dyad. Anyway, so here's our first one. Here's our second one. Initial conditions. We're gonna get this. This is gonna be for minor thirds, major thirds, perfect fourths, flat fifths, and then how we get the other 5 is we just invert. And the reason you get 5 is because when you invert tritones, you just get the exact same sequence. So when we invert perfect fourths, we get negative 5/6 plus 5/6 compared to 5/6 minus 5/6. And instead of perfect fourths, we're going to get perfect fifths. Instead of minor thirds, we're going to get major sixths. Instead of major thirds, we're going to get minor sixths. instead of semitones, we're going to get major sevenths, and instead of whole tones, we're going to get minor sevenths. And so how we get the other 144 is you can change any of the initial conditions as long as our third derivative, I'll just write this here, third difference must not be octave. Ugh, sorry. All right, our third difference, meaning this is going to be our first, second, third diff. This number right here can never be a root or an octave, meaning it must be greater than 0 and less than 2. And that's just because anytime we have a constant of an octave, we're just going to get octaves. And that's just going to make things more complicated. So anyway, you could change this to anything, you know, perfect fourth, perfect fifth. You could change this to anything, major sixth, minor second. It's going to change all of the numbers in front of it, you know, but that's how you get, you know, A, B, C, D in your cubic coefficients.